This is lesson 2 on modulation. It's the second lesson in the wireless communications portion of this course. And we started last time with a review of some of the basic concepts of radio frequency wireless communication. Now we're going to talk about modulation, and then we will conclude with a section on the use of antenna and also one on the link equation. We talked about modulation briefly in the previous video, but the idea of modulation is to take a standard wave, a standard sine wave, if you will, and to methodically change some characteristic of the wave in order to represent information. And when you do this, you have two different signals. One is the carrier wave. That's a relatively high frequency standard wave, and that's the wave we're going to alter when we convey information. I say relatively high frequency, that is typically how we do it in satellite communications. It doesn't necessarily have to be that way in general, but that's what we use for satellite operations. Now, in addition to our standard carrier wave, we have the signal that represents the information that we're trying to communicate. And the term for the signal is the baseband signal. So we will say the baseband signal, the baseband wave, the input wave or the input signal, the information signal. Those all mean the same thing in the context of modulation. And we're going to take the information that's in the baseband signal, and we're going to use that information to determine how to change some characteristic of the carrier wave. You can see a very simple graphic, which we'll expand as we move through the module here. But the idea is that I take a combination of my baseband signal and the carrier wave. I go through some modulation process to produce the modulated wave. The modulated wave is what gets transmitted wirelessly. And then the demodulation process is, given the modulated wave and the knowledge of my carrier wave, I can once again extract the baseband signal, which is the information I'm trying to convey. The carrier wave has a very specific frequency, specific amplitude, a specific phase. This is what we mean by our standard version of the carrier wave. And for modulation, typically what we'll do is we'll pick one of those and we will vary it in order to convey information. And later on, we'll talk about how you might vary more than one at a time to do more sophisticated versions of modulation. But in its basic form, you take one of those characteristics and you change it. You modulate it in order to convey the information. And then the modulated wave is compared to the standard wave to extract the information and get back your baseband signal. In the graphic you see there, on the lower right-hand portion of the slide, you have our baseband signal at the top, and then you have an amplitude-modulated version of a higher frequency carrier wave, and next a frequency-modulated version of a higher frequency carrier wave. In the amplitude or AM version, you can see that we're changing the amplitude of that higher frequency wave, and the amplitude is varying right along with how the signal, the original baseband signal, varies. So when the amplitude of the signal gets large, the amplitude of our carrier wave gets large. And likewise, down in the FM modulated version, when we have an increase or a relatively large amplitude of our signal or baseband, we have an increase or a large number of frequency for the modulated FM wave. So we are increasing the frequency of the carrier wave when we have a high amplitude baseband signal, and we decrease it when that amplitude goes low. For digital communications, which is more what we talk about for satellite operations in the context of this class, our baseband signal is a digital waveform. So it's high and low levels. It's ones and zeros as opposed to a continuously varying wave like we saw in the previous slide. So when we do digital modulation and we have a digital baseband, then the way we shift the amplitude, frequency, or phase of the carrier wave is done in a discrete manner. And so, for example, if we're doing amplitude shift keying and we only have two choices of the baseband signal, a 0 or a 1, then we move between two choices of amplitudes for the modulated version of an amplitude modulated wave. When we do this, we call it shift keying. That's the discrete or digital version of modulation in this case. So amplitude shift keying is going back and forth between two different amplitudes based on whether the piece of information is a 1 or a 0. And in the figure here, you can see that our amplitude is some amplitude or 0. And this is a very extreme version of amplitude shift keying, and it actually sometimes has its own name called on-off keying. So on-off shift keying is basically I'm going to have a wave or not, which is equivalent to saying I have a wave at a certain amplitude and then the same wave at a 0 amplitude. So on-off keying is an extreme version of amplitude shift keying. But the basic concept of shift keying is we go between two different choices in the basic version. Same thing with frequency shift keying. You can see we are using either a relatively high frequency wave for the ones or a lower frequency wave for the zeros. And then for phase shift keying, you can see that at the start of each bit, whatever the phase is of the wave is conveying the information. So you can see that at the different transitions, whether or not the absolute value of the phase is at 0 or 180 in this particular case, that's one form of phase shift keying. So here's some other examples. I've just written up another series of ones and zeros, and you can see my version of what the modulated shift keyed carrier wave would look like for some of the different techniques. So amplitude shift keying, on-off shift keying, which is the extreme version of ASK, frequency shift keying, and then at the bottom, phase shift keying. This is something that you ought to be able to do. You ought to be able to take a bit stream and sketch out the wave. And conversely, if I gave you the wave and I told you what the shift keying technique was, you should be able to extract the bit stream itself. We'll practice that during the in-class portion of the course. There's a quick summary, analog modulation versus shift keying version of modulation. You can see the difference in the signals. It's either a continuous or discrete signal. And then in each line, the amplitude version, amplitude modulation, amplitude shift keying. Line after that, the frequency version. Line after that, the phase version. Another interesting aspect of modulation is something known as the modulation index. So the idea of modulation, again, is to change the characteristic of the carrier wave based on the content of the baseband wave. But we haven't really said how much of a change we should have in the carrier wave. And you can imagine being more or less aggressive with how much you're changing that wave. So for example, if we're using amplitude modulation, if there's a change in the in the baseband signal, how much of a change in the amplitude of the carrier wave should we execute for that? Similar if we're using frequency modulation, for a given change in the baseband, how much of a shift of frequency should we use for frequency modulation? And so this notion of the modulation index is something that sometimes comes up in satellite operations because it contributes to the ease or difficulty with which you have in locking onto a signal. I can tune into the carrier wave at a certain frequency, but being able to really discriminate between changes in amplitude or frequency or phase is critical because that's how I'm doing the demodulation process. That's how I'm extracting the information. So modulation index is an important factor for this reason. You can see an example of changing the modulation index for amplitude modulation. The math is more complicated than what I want to go into here in the presentation, but I think the graphic sort of speaks well to the effect. As I increase the modulation index, I am, and you can see the original baseband there, you can see how more and more drastic the change in amplitude of the carrier wave is for an amplitude modulated wave. And in fact, in that bottom one, I've gone too far. When you look at the modulation index of 0.3 to 0.7, you can see that I'm increasing how aggressively I'm changing the amplitude. And if you look at that 0.7, you can imagine, well, if I keep going, at some point, I'm going to hit zero amplitude on my modulated wave. And if I go beyond that, I'm going to get a negative amplitude. And if I get a negative amplitude, do I really know if it's negative? Because it's going to look like positive amplitude with a phase shift. And if I'm not paying attention to phase, then I have a problem. It just looks like a positive amplitude. And so, is it really going down further, or has it increased again? And I've lost that information. And so you can see that that's what's happened actually for our last plot for the modulation index of 1.3. You can see that moving left to right, the amplitude gets bigger and then smaller, and then it gets really, really small, and then slightly bigger again, and then smaller. So that slightly bigger again isn't actually slightly bigger, it's gone negative, and the wave has flipped. And it can be very difficult to figure that out. And so you can be too aggressive, is the point. You want to be aggressive enough in order to be able to lock on to the signal and do the modulation process, but you don't want to be overly aggressive because you can basically distort the signal in the process of doing this. So another interesting twist on modulation, when we were doing shift keying, the description of shift keying, I sort of said, we're talking in binary, and so you're going to have two choices of amplitude or two choices of frequency or phase. But you can actually get fancier than that. If you, rather than taking the information from the baseband, sort of the string of bits, one at a time, you can imagine taking them two at a time. So for every 2 bits, I would then have 4 choices. So maybe I have 4 amplitude or frequency or phase choices that I shift between. You can see an example here in the slide of what's known as quadrature phase shift keying. And that exists, and it's used extensively. And this is an example of taking 2 bits at a time and converting that from a modulation perspective to one of 4 different phase options. So rather than just being 0 or 180, you can imagine 0, 90, 180, or 270. In this particular case, they actually shift all those by another 45 degrees. But the idea is you have 4 choices rather than 2 choices. And you can even be more extreme. You can take bits 3 at a time and have 8 choices. If you can imagine the more you do it, the more sophisticated the equipment needs to be. But you also have to have better sensitivity because you have to really be able to tease out the differences in or amplitude or frequency in terms of these discrete levels. And remember, the whole reason we went discrete to begin with was to separate the levels to be immune to noise. And so we're kind of now going back in the other direction. And so there's a limit that you'd want to go. But you can take more than 1 bit at a time and have more than 2 choices if you want to do more advanced versions of shift keying. In fact, you can mix and match these as well. You could have both amplitude and phase shift keying. And so depending upon the bit structure, I could change the amplitude and the phase simultaneously and work those problems in parallel in order to get more bits per unit change in the carrier wave. Now, just a little bit about some of the modulation or communication equipment we use for satellite operations in Santa Clara. Here is some of the equipment used on the ham radio channel. This is used normally for the satellites we operate to broadcast a periodic, very low data rate beacon. So you'll hear us talking about the beacon channel, the beacon signals. And you can see on the right, there's the board, little tiny beacon radio, very small board that's on board the spacecraft. And then on the bottom, you can see the equipment that you may have seen in our ops room. We have an ICOM radio and a little device called a terminal node controller that I'll talk about here in a second, but that's the stuff that's in the ops room, sort of on the receive end. We use the beacons only for one-way transmissions from the satellite to the ground. So the top board there is a transmitter, and the equipment on the bottom, although it can be used for both transmit and receive, we use it as a set of receive equipment. So this particular system is a bit of an oddball. It uses FM modulation, and it does that on a UHF carrier wave. So we're shifting the frequency of the UHF carrier wave, and typically the frequencies we have for our beacons are sort of clustered around the 435 megahertz point, plus or minus a megahertz. Most of the center frequencies are in that range. But the interesting thing that happens here with the ham radio transmissions, and it isn't overly common elsewhere, but it has a great heritage in our own personal computer industry, is that the ones and zeros that we're trying to broadcast, rather than using those and doing frequency shift keying, as you might expect, we use those to do frequency shift keying at the audio level. So using audio frequencies, which are much, much lower than the UHF 435 megahertz frequency. So we're not doing direct frequency shift keying of our primary carrier wave. That's not what we're doing. What we're doing is we're frequency shift keying a much lower wave, and then we've created this new wave at a lower frequency, and we use that as the equivalent baseband to do standard FM modulation of the UHF wave. We do this in a two-step process. You might say, well, why would we do that? And the reason is that there's a heritage of equipment and techniques for doing it this way that comes out of the PC industry with modems. And with modems, what was attempted to do and worked quite well was we took the ones and zeros that we wanted to communicate and we modulated audio waves, audio frequency waves, much like is happening in the first step here, in order to broadcast them over phone lines. And phone lines were specifically built for people to talk through, and people talk in standard audio frequencies. So here is a channel that was optimized, and all this infrastructure centered around the communication of audio frequencies, and the computer industry took advantage of that. And they said, well, we might as well use, we have digital information, so we're going to do a shift keying approach. But there's no need to shift key full-blown radio waves, microwave frequency radio waves, because we're not doing satellite communications. I don't need to worry about absorption through the atmosphere. I'm trying to get these through phone lines, and phone lines are built for audio frequencies. So they frequency shift keyed audio frequencies in order to get this information to the phone line. So now the ham radio community has used that, and a lot of that equipment and those techniques are very simple, very inexpensive to use, a lot of built-up infrastructure and knowledge centered around that. So they do that as a first step, and they do that in a process that typically is executed in a piece of equipment called a terminal node controller. And this does that first phase of modulation, and it also does a lot of command and data handling functions like packetization and things like that. So for the StenSat beacon radio there on the top, it does that sort of all on the same board. So there's some command and data handling functions that are going on. Then there's this first step of frequency shift key modulation that's going on. And then there's a regular FM modulation of the 435 megahertz wave in order to broadcast that from space down to the ground. And on the ground, we use our ICOM radio to do the FM demodulation. And then the AFSK, the audio tones, and the depacketization is done in the terminal node controller. Another piece of equipment that we use a lot is the MicroHard series S-band transmitter. Shown here is the 2400, but there's now 2410 and various versions of these. But this is what was first used in GeneSat, and a version of this has been used in all the other, or most of the other satellites that Santa Clara has controlled, certainly the NASA ones. This was not ever built for a spacecraft application. It's used for just standard terrestrial wireless networking. But through analysis was determined that it might be something that would work as a very low-cost way of communicating information from inexpensive spacecraft to ground. And so here you can see some of the specs. Its power level, the kind of modulation it uses. It actually, if you use it for its intended purposes of wireless networking, it operates in what's known as the unlicensed band. So it is so mundane and trivial from a use of the spectrum point of view that if you buy this and it's gone through an FCC certification to make sure it adheres to FCC specs, But I don't need a license now to use this because it's relatively low power. As it turns out, we broadcast the results of this radio through an antenna system, 3 meter parabolic dish that really focuses that energy. And so, in the direction that the antenna is pointing, we actually blow the power spec for use of this in an unlicensed manner. And so when we use it, because we are using it through a very high gain dish antenna, we actually have to get a license for this. It no longer is a piece of unlicensed equipment, given the way we use it. And so we have a full-blown FCC license in order to use this particular unit with a 3 meter parabolic dish. It turns out that this also does frequency hopping. And it turns out that all these things we've talked about in wireless communication happen on this board, but this board also does some data handling functions. So in the context of one component, we have multiple functions. We have some wireless communication functions, and we also have some data handling functions. So it does some forward error correction. It does encryption. It does packetization. A lot of those things that we talked about in the last portion of the TT&C module. So in summary, modulation. We are changing a characteristic of a wave, sometimes more than one characteristic in a more sophisticated version. But we change it in a way to convey information, and then in demodulation, we look to see how it's been changed in order to extract the information back. We can change the amplitude, the frequency, the phase, various combinations of these. We can do it in an analog way or in a digital way. When we do it digitally or in a discrete way, we usually use the term shift key for that. And then transmitters generally perform the function of modulation, and receivers generally perform the function of demodulation. And sometimes we use the term transceiver, which means it can do both. That's the end of our modulation section. So if we take a step back and think about what's happening to model the process of modulation, um, a somewhat simplistic version of it is that it's really multiplying those two signals. And so I want to walk through this simple version to point out a few features of things we see in the modulation process. So our two signals are the baseband signal and the carrier signal. And the carrier signal starts out usually as a sine wave, a sinusoidal carrier at a very specific frequency. And we'll assume it's a relatively higher frequency than the baseband signal. And then the baseband signal is some sequence of ones and zeros, or if it's an analog baseband, then it might be a continuously varying signal that's, in general, the sum of a lot of different wavelengths. So you can see that when we multiply those two waves together, we're going to get an expression, and I want to walk through and show you the features of this expression. To do that, we're going to pretend for now, just for the purposes of walking through the math, that the baseband itself is a sine wave. So it's a very specific frequency as opposed to the sum of a lot of frequencies. But by doing this, we can get an idea of mathematically what's happening through this modulation process. So I've got, for now, a relatively low frequency sine wave for my baseband and a relatively high frequency sine wave for my carrier wave. And if I take those two signals and I multiply them together in order to get the modulated signal, you can see a few lines here of just manipulating the math. I take the two sine waves with some amplitude and I multiply them together. And you can see the bottom expression there. I have some coefficient, which is half of the product of the two amplitudes of the individual waves. And then I get an interesting expression when that comes out from multiplying two sines. I get a cosine wave minus another cosine wave. And an interesting feature of this is that you can see what the frequencies of the cosine waves are. They are the carrier frequency plus and minus the baseband frequency. And this is something that you may have heard about before. It's called the heterodyne principle. When you mix or you modulate two frequencies together, you're going to generate two new frequencies, and those frequencies are the sum of the differences of the original two frequencies. So if I look at that wave again, and I think about this wave in terms of a frequency plot, so what's the amplitude of the wave as a function of frequency, you can see on top, there's my initial input. I've got a pure frequency at the baseband frequency and a pure wave at the carrier frequency. But when I mix them, when I modulate them, the resulting waves are at the frequencies of the carrier wave plus the baseband wave and the carrier wave minus the frequency of the baseband wave. So I've gone from two specific frequencies for the baseband and the carrier to the output, which is two new frequencies centered around the carrier. So here's that expression again. And what I've done is I've just gone to MATLAB and done a simple modulation process, so a multiplication of those signals and plotted the results. So here you see, again, relatively low frequency baseband wave. I just chose 20 radians per second just to show you something. High frequency carrier wave, that's 600 radians per second, so much higher frequency than the baseband. When I multiply them together, you can see that that wave is conveying the information of the baseband by changing the amplitude of the high frequency carrier wave. So that's kind of an interesting way of thinking about it. And the component frequencies in that modulated wave are actually at 580 radians per second and 620 radians per second. So when we walk through this process, I'm going to take the carrier wave and the baseband wave. I'm going to multiply them together to get the modulated wave. And so there's the mathematical expression for the modulated wave. And in frequency space, there are the pure frequencies that have been generated. And they're up close to the carrier wave. And they're offset by a little bit, offset higher and lower by an amount of the baseband frequency. And so what we'll do in practice is we're going to filter out one of those. And so for the purposes of this demonstration, I'm going to get rid of the higher one. Turns out that both of those waves carry the information that I want. The information I want is the baseband wave. And I see the baseband wave represented in the amplitude, which I get for both of those, as well as the specific frequency. So I don't need both of them. They are duplicates of each other from an information point of view. So I'm going to filter one out. That's going to make my job easier as we move through this process. So I modulated the carrier wave with my baseband wave, and I generated two new waves. And those are called sidebands of the carrier wave. And I'm going to get rid of one of the sidebands because the sidebands are duplicates. In this case, I'm going to get rid of the higher frequency one, although you could just as easily have gotten rid of the other one. So I'm filtering out the higher frequency sideband. So I'm left with the lower frequency one. You can see that mathematical expression there in the second bullet. And now to demodulate, all I do is I multiply once again by the carrier wave, just like I did at the beginning. So I modulated the baseband wave by multiplying it by the carrier. Now I'm going to demodulate the modulated wave by multiplying it by the carrier. So I have the filtered modulated wave in the second bullet, and now in the third bullet I'm multiplying that once again by the carrier wave. And when I do that, I generate two new frequencies. And those frequencies are the sum and difference of the frequencies that I'm modulating. In this case, demodulating. So they wind up being, if you look at the math, again, some amplitude out there in front. And then I have two sinusoidals. One is at the baseband frequency, and one is at twice the carrier minus the baseband. So it's gone even higher frequency. But most importantly, I have the baseband frequency back. That was my original frequency. That's carrying all the information that I want, and now it's back down in the form of the baseband. It's scaled differently, but I can figure the scaling out. The important part is now I have my original bit stream back in terms of, and it's changing with a frequency that I want it to change. If you remember, we're representing signals as for spacecraft as time varying voltages, and the time variation is the frequency. That's the frequency content. So I've got that back by doing the demodulation process. And I simply filter out the high one because I don't need it. And so I'm left with the result through a low pass filter of a scaled version of my original wave. Okay, I get my original baseband back, but it's scaled. So here is the graphical sequence again from the time domain instead of time plots. Again, represented in Simulink, so you can see the original baseband and the original carrier. You can see our modulated wave, and if you look at the modulated wave, you can kind of go, yeah, I see that amplitude of the baseband being reflected in the amplitude of the carrier. And so that's interesting. The modulated wave I can make sense out of. And then you see the demodulated wave, which may be a little harder to understand. But that same information is in there. And then when I filter out the high frequency component, we basically get a copy of the original baseband. You can see its amplitude is different, but that is the original baseband signal. So expand my block diagram just a little bit. We showed this before, but now I'm showing it with filters. So first I'm going to filter the baseband just to get rid of noise. And then I'm going to go through a modulation process in the transmitter. I'm going to combine the baseband signal with the carrier wave to get a modulated version of the wave. But I may very well filter that as well. In fact, I may filter it because I don't want one of those sidebands. And then I get the modulated version at my receiver, and I might filter it for unwanted noise because I'm probably receiving what I want to hear, plus I may be receiving lots of other stuff at different frequencies. So I get rid of that other stuff. Then I go through a demodulation process in the receiver where I'm combining the demodulated, the modulated wave that I've received with the carrier wave to get the demodulated wave. When I do that, I generate two frequencies. I'm going to filter one of those out, the higher one. I'm left over with a scaled version of my original wave. So you can see modulation and demodulation happening at the transmitter and receiver, respectively. You can see that we're filtering. We're filtering for two reasons. We're filtering to get rid of the fact that we've received other signals that aren't really germane to what we're trying to do. But we're also filtering out signals that we generate implicitly in the modulation and demodulation process. We filter them simply because we don't need them. They're copies. We get rid of them and we make our life easier. So, given that we have that little bit of insight into what's going on in modulation and demodulation, sort of looks like this multiplication process with some filtering going on. We can extrapolate that on a qualitative level. So, a real analog baseband will have many frequencies, and so rather than being at a pure single sinusoidal frequency, it could be different amplitudes over a range of frequencies. And so, for example, you can see in the upper left-hand plot there, when we record voice, we see that the frequency content of voice is sort of below 3,500 hertz. Okay, it's a couple hundred hertz to 3,500 hertz or so, and it's a whole range of use of that little chunk of spectrum right in there. So when we modulate it, every single one of those sort of gets reflected. Okay, it gets modulated and generates its own difference wave, and you can see what we get is sort of a reflected version of that chunk of spectrum centered around the carrier wave. And we see that we have now two sidebands, a lower sideband and an upper sideband. And again, they are duplicates of each other. So we could filter one of those out and only have to really worry about the remaining one in order to do